Hello all, welcome to the video lecture. In this video, we'll be discussing about the multiple variable regression. Before we start with, let's have a brief revision of the linear regression that we have discussed in our previous class. Linear regression attempts to model the relationship between two variables by fitting a linear equation of the observed data. The observed data consists of independent variable and the dependent variable, and we will train the model or establish the model with relationship using the provided values of dependent and the independent variable as we have discussed in our previous class. And we can see here x as an independent variable, which is also taken as input, and y as dependent variable and taken as the output. Once the model is trained, we can predict the value of given unknown dependent variable. For example, we train the model with the advertisement cost and sales unit. Once we train the model, we can predict the value of sales unit when new advertisement cost is given. And the relationship between two variables is modeled by a straight line known as the base fit line, and a line of the best fit is a straight line that has the best approximation of the given set of data, and we obtain the best approximation of a given set of data when the distance between the line and the given points is minimum, or the best fit line minimizes the distance between the predicted value and the actual value. And the line is defined by two parameters, which is like the slope and the y-intercept. And the average square distance between the line and the given data points was calculated in terms of mean squared error. We can see here the MSC, which is nothing but the average of square of difference between the predicted value or the points on the line and the given data points. And the parameters are weights that define the slope and y-intercept, that is W1 and the W0 of the best fit line, or the line with the minimum FSC, is calculated using the gradient descent algorithm. And we can see here the gradient descent algorithm is an iterative optimization algorithm which is used to find the minimum of a function. And here that function is our loss function, which is MSC, mean squared error of the given data points, and the points on the line are the predicted points. And we can describe the principle behind the gradient descent as a climbing down a hill until a local or global minimum is reached, and at each step we take a step into the opposite direction of the gradient, and the step size is determined by the value of learning rate as well as the slope of the loss function or slope of the MSC. And each update is updated by taking a step into the opposite direction of the gradient, and the minimum point is reached when the gradient value is 0. And we define the step size as a negative of the product of the learning rate and the gradient of the loss function. Here this eta represents the learning rate, and this partial derivative dj with respect to wj, it gives the gradient of the loss function. And in gradient descent algorithm, we keep on updating the values of the weights or parameters until the minimum is reached or the gradient of loss function becomes 0. So the gradient descent algorithm becomes like we start with the initial guess for w or weight or parameter, say w0, and we iterate till the convergence. In each iteration we compute the value of gradient of jw or the loss function with respect to w or with respect to the parameter, and we update the wj or the weight to get the updated or new weight, taking the step in the opposite direction of the gradient. We can see here that we update the wj or weight from its previous value, and it is updated by taking a step in just the opposite direction of the gradient, which is defined by here. And this step size w delta of wj is determined by the learning parameter eta and the gradient of the loss function. And in each iteration we update all the weights simultaneously, and we have here w0 and w1, and in each iteration we update these two weights simultaneously. And the convergence is reached when the gradient of the loss function is 0, as we can see in the figure. Like this figure shows that the loss function with respect to w, we start at some point with some value of w, like we can see here the initial weight, and keep on updating the value of w until we reach the minimum point, this j min. And at this point the derivative of loss function or the gradient becomes 0. And as the step size is defined by gradient of the loss function, which is the partial derivative of loss function, as we calculate the partial derivative of the loss function, the gradient descent algorithm for the straight line is expressed as we can see here. Like once we calculate the partial derivative of loss function, the gradient descent of the algorithm for the straight line is expressed as, like, we repeat until convergence, we iterate the process, and we keep on updating the value of w0 and w1. And here we have the previous w0, previous w1, and here the new term. This term just represents the derivative or the gradient of for the w0, and this term represents the gradient of the loss function for the w1. So we keep on updating until we reach the convergence, or we reach the point where the gradient of the loss function is 0. At that point, this value and this value will be 0. So we keep on updating the weights and get the loss function, and finally we get the two parameters, this w0 and w1, which are the y-intercept and the slope of the straight line, and that gives our base field line. So with these two parameters we can now calculate the new value, or we can predict the value of the dependent variable when independent variable is given. Like in this table, once we model the relationship between the size in square feet and the price of the house, we can predict the $1,000 price when new value of size in square feet is given. So we can see here, once we model the relationship between the size and the price on the basis of this size and price, on the basis of this given data of size and price, then we can predict the new value of price, or we can predict the price of the house on the basis of this size. So this is for the very simple example for predicting the house price. But in real time, the price of house is not determined by a single variable. So like the house it's determined with the lots of variables, such as number of bedrooms and number of floors, age of the house in years, and so on. So for this kind of data, we have to model the relationship between more independent variable or explanatory variable and the dependent variable. Like we can see here, we have got the multiple feature variables like size, number of bedrooms, number of floors, age of house, and we can use these variables or features to predict the price. Or first we have to model, and then we can predict the price of the house on the basis of these variables. So we have to go for the multiple variable regression or multivariate linear regression. The multiple variable linear regression attempts to model the relationship between two or more independent variable or explanatory variable and dependent variable or uh, response variable by fitting a linear equation to the observed data, and every value of the independent variable x is associated with a value of the dependent variable y. Like we can see here, it is similar to the simple linear regression, but with the multiple independent variables contributing to the dependent variable and multiple coefficients to determine, like we need to determine the multiple coefficients, and it's complex due to the added variables. So every variable of the independent variable x is associated with the value of dependent variable y, and formally we can define the model, or formally the model of the multiple variable linear regression given n observations is this. Let us say this model, this y subscript w, it as a product of sums of the weights or parameters and our independent variable or explanatory variables. And here this x0 is 1. And in order to develop the intuition about this function, we can think about like w0 as a basic price of the house, and w1 as the price per square meter, w2 as the price per floor, and so on. And x1 will be the number of square meters, x2 be the number of floors, and so on. Now, same as in linear regression, in order to fit a linear equation to the observed data, we need to calculate the parameters or the value of parameters that minimizes the loss function. So here is our model, which is represented by y subscript w, and it is nothing but the sum of product of the weights and the input variable or the independent variable x, and it ranges from this x ranges from 1 to n, and x0 is taken as 1. And here we have got the parameters which are w0 to wn, and our loss function is average of square of difference between the actual value of given data point and the predicted value. Now, same as in linear regression, we use the gradient descent algorithm to find these parameters, and this gradient descent algorithm it can be defined just as in linear regression, like we keep on updating the weights until the convergence is met, and the convergence is met when the gradient of the loss function becomes 0, and in each iteration we update the weights simultaneously. Here we have to update the total n plus 1 weights. You can see here total n plus 1, where n is the number of variables or number of features, and all the weights are updated simultaneously. As in linear regression, we have to update only two weights, w0 and w1, but here the weights, like this weights, total number of weights is n plus 1, and this is defined by this j0. We update the weights on the basis of the step size, and the step size is determined by the learning parameter, this eta, and the derivative of the loss function or the gradient of the loss function. And here n greater than 1, the linear regression becomes multiple variable regression. So we have to determine the step size for the multiple number of features, and here the step size is determined by the learning rate and gradient of the loss function. The gradient of the loss function is calculated by the partial derivative of loss function with respect to weight defined by the feature. So the weights are updated by calculating the partial derivative of loss function with respect to each weights. Like here we have got 3 weights, so these are obtained. Like you can see here, these relations gives us the partial derivative. This is obtained from the partial derivative of the loss function with respect to each j like this is, and this expression gives us the partial derivative of, or the partial derivative or the gradient of the loss function for w0, and this gives us the partial derivative or the gradient for the w1, and so on. In this way we can model the relationship between two or more independent variables and a dependent variable by fitting a linear equation to the observed data, and every value of the independent variable x is associated with a value of dependent variable y, and once we get the value of independent variables, and we can predict the dependent variable y or the output of the variable using this model. And this is all about the linear regression, and in next video we'll be discussing about the logistic regression, which is the classification problem, or which is used for the classification problem.